purpose of this video is to go over another example here with regarding partial fraction expansions. And as a quick summary, the goal is to have our transfer function in this form where you have the zeros or the roots of your numerator on the top and the poles, which is the roots of your denominator, on the bottom. And by applying a partial fraction expansion, we are going to rewrite this expression in this form, which is more user-friendly for our inverse Laplace. Now, the goal here is to find the poles, and the poles, when we do that, so the roots of our denominator, they can come into three flavors: real and different, complex numbers, or real and equal, and can be a multiple of them. So in previous videos we saw an example of a real and different, as also an example with a complex number, and we apply this cover-up algorithm. And this video is going to focus on the real and equal or multiple poles that are the same. And we're going to investigate, or we're going to learn two ways of doing that. And to understand these, I think it's better if we do it over an example rather than being too theoretical about it. So way number one, where we have, let's say we have this transfer function, we got it out of our circuit, and one way of doing that is to factor out one of the poles that it's multiple, so this s plus 2 comes out. And now I apply, these are real roots, and I apply the cover-up algorithm just on this portion of my equation. And if I do that, I get the 6s minus 2 over s plus 2. Okay, so now the second step will be to multiply these 6s by this pole and these minus 2s plus 2 by that pole. And I get the following expression. And now I apply the cover-up algorithm on this first part over here, and I get my final answer. Alright, so way number two, it's slightly different. We're going to rewrite our equation right away with our poles separated with the respective k1, k2, and k3. And here it's important to write them in this fashion where you have your s, and then the multiple poles here, you're going to split it in k2 s plus 2 squared, and then you leave the s plus 2 in the last index k3. For k1 over s, you just apply the cover-up algorithm, straightforward, and you get 3 over s. For the s plus 2 square, we are also going to apply the cover-up algorithm, as we have been doing, and you get minus 2. And I'm putting the minus here so we can know or notice that it's a minus 2. If I put there, normally we forget that minus, just to make sure that we see that it's a minus 2. And then for k3, we're going to apply the derivative of our original function, so this 4 times s plus 3 over s, and after applying the derivative, we substitute s by our pole, which is s minus 2. Alright, it's important to just go over this derivative really quick so we understand how it's done in this particular case. And it's by using this quotient rule, where we do the g of s, the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator with the denominator square on the bottom. And if you do that, you get minus 3 for your k3, and you substitute that back and you get exactly the same answer as way 1.